Okay, here's another example. Let's take a quick look at a case where we apply the law of total probability in a setting that is very easy to simulate. So suppose we have three bags, each containing, let's say, 10,100 marbles, but with different proportions of red and blue. So you can see the different proportions there. They should all add up to 10,100. I forget why I chose that exact number. And we are going to one, choose one of the bags at random, and then two, pick a marble at random from the chosen bag. And the question is, what is the probability that the chosen marble is red? So let's look at the solution. Let's define two events. R, the event that the chosen marble is red, and B of I, the event that bag I was chosen. Then remember, we're looking for the probability of event R, that the marble is red. The total, so this is a perfect place to apply the law of total probability, as we see here. So the probability that's red is the probability that it is red given that bag one was chosen times the probability that bag one was chosen, plus the probability that is red given that bag two was chosen, times the probability that bag two was chosen, and so forth for bag three. Direct application of the law of total probability. Since each bag is equally likely to be chosen, the probability of bag one, bag two, and bag three are all independently one third. The red probabilities for each bag are given in the problem. They're 75, 60, and 45% when you form the ratios. So given all of that, you just plug them into the formula, and the probability is 0.75 times a third plus 0.06, or sorry, it should be zero point 0.6. I have a mistake there, times a third plus 0.45 times a third, which gives you zero point 0.6. So I set the numbers up so that it came out nicely. The probability that the marble is red is zero point 0.6. And I didn't say this for the previous segment. I have some code in the slide deck and I have it in the Dropbox. But you should, for that case and for this case, write a simple simulation and verify that the result is the result that you get analytically, and ask yourself some questions about the simulation, such as if the simulation is based off of a random number generator, how does that random number generator work? How good is it? What's its period? In other words, how many samples can you take before they repeat themselves? Are there correlations in the random number generation stream? How do you seed it? How many samples do you need to get what level of convergence? So, how do you know when you've gone far enough? And how do you know if you are converging toward the right answer or the wrong answer? How do you implement these things efficiently on a computer? I mean, there are all sorts of questions that we could ask. What rate do you converge to the correct solution? So, this class explores the relationship between the analytical and the computational solution and a lot of the challenges about the computational solution when it's the only path forward. And I want you to start thinking about some of these questions, and it's good to program these things in order to start to gain an intuition and even know what questions to ask.